Hey everybody, Dr. A here, and in this video we're going to be exploring an example of bearing stress. So let's take a look at the given information. Here we're being asked to compute the bearing stress at the support B, which is an 18 by 14 bearing plate. So what we have here is this simply supported beam that is subject to this linearly varying load, or a triangular load. It goes from 0 at point A up to 0.5 kips per linear foot at point B. The beam is 12 feet long, and the bearing pad that's 14 inches by 18 inches is right here, okay? So what do we need to do to solve this problem? Well, we know that bearing stress, sigma sub B, is a force divided by a bearing area. Now, we were pretty much told what that bearing area is. It's 18 inches by 14 inches. So pretty straightforward. I'm going to go ahead and calculate that, 18 by 14. So that's 252 square inches. So we have the bearing area. What we really need is the force, okay, that is bearing down on that area. So here, that force is actually just going to be the reaction By, okay? So at this point, it's really just a statics problem. We're analyzing a simply supported beam and we're calculating the reaction By. So let's do that. Let's look at a free body diagram of this entire beam. And we're going to draw this linearly varying load here. Okay. And this is 0.5 KLF. And the whole thing is 12 feet long. And we know that we have an AY, an AX, and a BY here, and what we're really interested in is BY. So if we want to get BY, it's pretty straightforward. We're going to say sum of the moments about point A equals 0, and the reason why we're summing moments about point A is so we can solve for BY directly, because that's what we need. We just need BY, okay? So we're going to perform this equilibrium calculation. We're going to say negative 1/2 times 0.5 KLF times 12 feet times 2/3 of 12 feet, okay? And then we're going to say plus BY times 12 feet equals 0. Now, for those of us who are a little rusty from our statics, why did I do this? Where do these numbers come from? Well, first, this 1/2 times 0.5 KLF times 12 feet, that is the equivalent point load of this triangular load distribution, okay? So what that is that is like this force right here from statics. We can call that F equiv, okay? And this is equal to the area beneath the load diagram. So this is quite literally this triangular area, 1/2 base times height. And why is it negative right here? Is it negative because it's pointing down? No. It's negative because this triangular load is causing a clockwise rotation about point A. And a clockwise rotation about point A would be negative, since we say counterclockwise is positive, okay? Now, where does the 2/3 times 12 feet come from? Well, that's the moment arm, okay? So this right here is our perpendicular distance, or our moment arm. So that is this distance right here to point A. That's 2/3 of 12 feet. So if you remember, the centroid of a triangle is located at 2/3 the distance away from the tip of the triangle, or 1/3 of the distance away from the face of the triangle, okay? So that's where the 2/3 comes from. Now, we then say plus BY times 12 feet, because this BY is causing a counterclockwise tendency of rotation about point A, if you just look at BY, and its moment arm away from A is the full 12 feet, okay? So we perform this calculation, and we get BY equals, and I'm going to punch this through in my calculator along with you, so I encourage you to do it with me. Okay, so I get 2 kips reacting upwards, okay? Now, that's a compressive or bearing force, and so finally, if we want bearing stress, we're going to say sigma sub b equals 2 kips divided by 252 square inches, and what we get is 0.00793 KSI. That's kind of a small number, so how about we convert to PSI, and of course we would get 7.9, and I'm just going to round that to 3 sig figs, 7.94 PSI, pounds per square inch. Okay, let me make my box a little nicer. So that concludes this example, and you know, I like this example because it helps us refresh some topics from statics that we might be a little bit rusty on. But again, that concludes this example. If you found this helpful, please hit like and subscribe, and be on the lookout for other content like this. Thanks for watching.